Thanks everyone for joining today. My name is Zach Sample here at XP Solutions, and if you haven't joined us before or haven't heard about XP Solutions, just so you are aware, to sum it up, we have a long history of providing original high-performing software solutions. One of those we're going to look at today. And one thing that I personally pride myself on is our ability to support our users and to educate the community, something that I was involved in before taking on the role as product manager for XPDRAINAGE, which we'll look at today. So this is the second webinar in our series on detailed design. It's kind of the general idea. Well, this is, I guess, kind of the meat and potatoes, if you will, of the design, the runoff reduction and sizing portion. So to talk about that, well, we need to cover, I guess, is perhaps the unified stormwater criteria and runoff reduction. What are those ideas? And we'll review a bit from last time kind of how those concepts really are the framework for which we operate. So the traditional sustainable drainage approach is really that unified criteria approach. We'll look at how XPDRAINAGE kind of set this through a workflow, and then ultimately jump into some real project examples. I have a few things lined up today that are quite exciting. So as described by the Georgia Stormwater Manual, runoff reduction practices are stormwater BMPs used to disconnect impervious and disturbed pervious surfaces from the storm drain system. Okay, so that's perhaps a longer way to say we don't want disturbed areas. We don't want pollution to wash into our storm sewer system. So pollution is going to accumulate on impervious areas or disturbed soils. So we're looking at targeting with this practice by implementing these items pollution, and yes, targeting runoff rates and volumes as well. But as we spoke about previously, the volumes that we're going to hold on to and infiltrate and treat, we're making an assumption that that first flush, that minor volume event, is carrying with it all the pollutants. So runoff reduction is kind of what we use to talk about sizing specifically our green infrastructure, our pollution removal facilities. So then what would be that unified stormwater sizing criteria? Well, it's the runoff reduction and everything else. So again, according to the Georgia Stormwater Manual, the unified criteria method is an integrated set of design criteria for stormwater quality and quantity that addresses an entire range of hydrologic conditions. So that's the important part here, is that we're looking at the entire range of rainfall, frankly. So the very minor events, we're going to have the most most polluted runoff occur. That's the runoff reduction. But then everything else, all the way up to 100-year or more events, those are going to be defined. I've already mentioned that runoff reduction. Okay, that's that first water quality volume component. And then we get into those higher events, channel protection, overbank, extreme flooding protection events. So that's kind of that 2 through 100-year event range. So we'll see, as we talked about last time, our facility design constraint. So our typical way to approach a project really is that unified criteria. We retain the water quality event, and then we bypass and attenuate the higher protection events. I worked through a typical, this is actually a real-world budget and project, kind of a smaller project, probably for many, but worked through kind of how we might bill out a project and really the time that you're actually going to spend on it, from my experience. So we're going to look at whittling down the bulk of that time, the real design, calibrating. We want that to be as close to zero as possible. Okay. And before we move on, now that we've seen kind of what that unified criteria and what that runoff reduction criteria is, I want to have a poll. So the question is, How often do you have projects which use the runoff reduction sizing constraints, sizing methods? So go ahead, there's everything from, hey, I've never done this, I do this every once in a while. Maybe you have 2 monitors and maybe you're designing on the side right now. So let's just take a second and you can click through there and we can really see kind of everyone's workload on this particular design. All right, great. Looks like we have most people here have filled it out, so let me go ahead and close that poll. And I can share. So it looks like we have a pretty even split across the board. Some people have not done this as much. Some there's a handful that sounds like they're even working right now on a project. So most people overwhelmingly have seen this, have used this on a regular basis. So that's what we're going to get into now. With really the bulk of today's work is talking about all aspects of the unified method, but in particular that runoff reduction component. So if we look back again from last time at the XP drainage workflow, the focus on how we eliminate the majority of bulk on our budget. The most time we're going to spend is on that modify and compare portion of our workflow. So we have that question I asked last time, what if we could automate this part? So there's many things beyond just a runoff reduction automation that we can look at, and we'll look at today. But that's the focus of our discussion. So to keep things brief, I could obviously talk for quite a while on this subject, but the items we're going to touch on today: outlet controls. Okay, we have outlet calculator sizing, complex structures, automated stormwater sizing, so not just the outfall or outlet, but the actual facility itself, local facility sizing, and global site-wide automated sizing. We have the ability to automatically size our pipes through our system. That's going to be based on rational Manning's equation, for really a good place to start, if anything, but you can use that to size your system, as well as a pretty robust rainfall selection. So we have multiple different rainfall events, and we'll look at that. So let's jump into the model. So we can see here I have a model from last time. Just to orient everyone, I will deluge the site one more time, give us an idea of what's happening on this site. All right, so we have this area, so I'm going to call out this catchment, something we defined last time, all drains to this southwest corner. And one of the layout ideas that I had discussed last time was, since we have ability to kind of automate our design, we just need to plop controls where we want them. Okay, so in this case, I just plopped in, I wanted a bioretention system here. Okay, so I didn't really give it too definite of shape. I really just kind of put that area down, and you can see this is what we're looking at. This is our the physical description, the dimensions, right, of our facility, with the different filter layers and whatnot already populated. So we have our bioretention, this rain garden, that we want to treat this catchment. Okay, so what I said before was, well, what's the next step? Well, let's size this facility. So a couple ways we could do that. So the first, using this sizing calculator. So select this button, and we have, by default, it's going to jump us right into the runoff reduction tool, which we'll look at in a second. So you can see we have a number of different options here. By default, we're going to use runoff reduction to size, probably the fastest, most robust. But we have several different options. So we could, the most basic, most straightforward might just be to scale. So maybe I want to just simply scale the facility, larger or smaller. And then quick storage estimates, so that you'll see the scale. I can put in a percent size, bigger or smaller. We'll get into what the design level updates are in a second. Quick storage estimate is maybe kind of a step above that. So it's pretty clear what the scale does. Put a number in and it will amplify or diminish one of those value sets. Quick storage estimate, a little more robust. So we could use this tool to enter in some constraints. So perhaps I know that my area is 1.14 acres, and I know maybe the existing flows on that part of the site. I want to limit, the discharge leaving this facility to a certain rate. I can enter that in, maybe 0.44 cubic feet per second. Okay, and we can select our rainfall. We'll look at rainfall more in a little bit. But select what rainfall, HUF, SCS storms, and it'll give you an estimate, kind of a window based on those storms of what volume size to adopt. And then we'll explore in a little more depth, runoff reduction is one of the options. So I haven't yet gotten to design level. What does this mean? So we can size the volume that's required based on the exceedance level. That would be the top of the facility. You'll see here, I'm actually showing this software right now. You see the cover level doesn't say exceedance. This is actually a change we're making right now in our release, which is going to be coming out here probably end of the month. So we'll have, this will again say exceedance level, but we have exceedance level freeboard and lowest outlet. So pretty sophisticated. We could just say size this facility to be full to the brim. That's what the exceedance level would say. In my case, I can't exceed a 6-inch freeboard at this facility. So I could select freeboard. So you know what, I need to fill this up, but make sure there's at least 6 inches on the top that's open. Or one thing that I quite like is if you have outlets. So in the real world, perhaps the freeboard isn't a constraint, is you have some sort of outfall weir. So it will find the lowest kind of outfall, and it will size the volume under that. So you have a high flow bypass, and then, well, I can't occupy any stage level above that, so size just everything below my high flow bypass. And then, of course, when I get into my more major events, the bypass will work as expected, and I've sized for the more minor events. Okay, so we might just look at the freeboard for now. And given the stormwater controls, we have a range of different ways you can manipulate that. So we can see here that we can update simply just the areas. Right? I just want to make this plan area larger. Okay, well, you could also make the facility deeper. Okay, that would maybe be in the case of ponds or some facilities where you have a lot of vertical room to play with, or perhaps you have a kind of a fixed top perimeter around a given area, and you want to really just change kind of the side slope. So I want to change the base area so that the volume is correct. So all those you can do, I'd say probably just changing both top and bottom areas, just making the whole thing bigger or smaller, is probably the most common. So a lot of explanation, basically to show all the different options that you can use. Okay, so it's quite robust. From what I've found, from what I've heard from people, is that really the default, just making the areas bigger, runoff reduction, probably the most commonly used thing. So we can now get into runoff reduction calculation. So most of you are pretty familiar with this already. We have two different options. So the first one, this is the default. I think we have even listed everywhere from the the Georgia manual, New York, Carolinas, a lot of, especially the East Coast and the Southeast of the U.S., this, what we're calling runoff reduction equation, is what's used. Now we also have another method called the simple method. Okay, just another calculation, maybe a little less frequently used. So we're going to use this calculation, and we could manually enter information in here. So I know that my site's 17 acres. Well, I could manually change that and put in a percent impervious, what have you. Well, why do that when we can automate this using all of our already input areas? So we have all these inflow areas, and in that inflow, something we've set up, we already have a percent imperviousness for all the different portions of our site. So all that we have to do is just enter in our precipitation depth. Depending on where you're at, this might be 0.8, this might be 1, 1.2. Let's just use 1 for now, and we'll calculate. So pretty simple. Right at the top, you can't. So what is kind of the report? So we have a target volume, volume achieved, and really what's missing. So outcome, well, that's failure. So you'll see here that we have almost 3,400 cubic feet of volume that's going to wash off our inflow area. Now we can look at the details here. So if you wanted to just directly report this, okay, we could show all columns, or if it's easier to see, we can reduce that. So this is kind of a direct report as well as this design tool. So here we have almost 3,400 cubic feet of volume. And our facility, when we first drew it, it's quite small. We need, probably a little over 3 times the size of that facility in this case. Okay, so what we'll do is if we click OK, it's going to adopt that 3371 volume. So you see it gets applied back to this calculator. Based on the areas, I want to make that bigger. Click OK, and you'll find that it will adjust my site. So that first case, I didn't really pay attention to how this was laid out. I just put something there. So right away, and again, in this model, we'll find that I made these objects and these volumes big enough difference where you can really see a lot of change. There's many cases you might find that actually is very little amplifying of these facilities, but it's not as interesting to look at in a presentation. So you can see a big change here. What do we want to do? Well, I maybe don't want this to be my final plan. The whole point of XPDRAINAGE is that we're linking together our calculation to what's in the plan, to how we're going to share this and communicate this with our team. So, well, maybe I can say, this is about the size I need. I have a better idea now that I sized that. Let me just replace the outline. Now I'll follow down kind of the perimeter of this area. Maybe draw something like that. I can have some sort of kind of terrace system in here. With this new layout, of course, I could use the calculator again, and I can see how closely I lie. You'll see maybe I'm still just a little under. Okay, well it can, I'm only 70 cubic feet under. Again, it can change that slightly, and we're done. So that's one way that you can size individual facilities quite quickly, quite easily. Many different layouts and designs kind of rapidly in succession, test them out and size them accordingly. So what if we wanted to do that for everything on the site? Okay, that's really the huge time saver, would be to analyze everything all at once. Okay, well, we can do that. So we might go up to this design tools section. A couple items here we haven't seen before. Well, water quality volume would be 1. Let's just say 0.8, just use a different value. I'll calculate. And here's the same table for all the facilities. So I stayed with the model we used previously where there's a number of different facilities on this real world project so that we could see kind of what you would more commonly look at, right? You might have 15 different facilities on a site. That's very common, very easy to accommodate. So what are we looking at here? So right away, we could, without doing anything else, right, report everything. Obviously, it gets a little busy. When we get a breakdown of, not only the stormwater control ponding zone volumes, the filter area, depths, void ratios, right? Everything you're going to want to report in kind of a final report or review, okay, if you're giving a report of this work to a city or county, or if you're the city or county reviewing someone's work, right? This is ultimately all the content you could ever ask for. Well, I don't really need to look at that during my design. I just want to see a bit of what inflow areas connect to what facilities and how much area that facility is going to provide. So the first thing I might do is look at this report and say, well, hey, success, I'm done. Really, I have the entire, that unified method being assessed. Okay, so let me just go back to the model. So not only do I have these individual controls, I have everything from porous asphalt to swales to rain gardens to this pond. And in particular, this pond is not something that I'm going to be using for my kind of green infrastructure. I'm not going to be treating pollution with this. Okay, this is that 100-year event extreme flood detention pond. So if we go back to my design, let's go back here. I don't want to apply the pond towards my goal. So now you can see, well, we failed, right? Clearly, without the pond, we aren't storing enough. So we're going to need to upsize these facilities. Again, I mentioned how we're going to need to upsize them 2 or 3 times their current size so you can really see a big difference. So I'm not assessing the pond. That catchment I also don't want to look at. Okay, so we can pick and choose what objects we size, what objects we include in this report. Now the swale, we can see here that this swale, it's doing too good a job. So it can hold more volume, a little over 8,000 cubic feet of volume. It can hold more volume than it's receiving. So here's the swale, right? It's only receiving 6,500. But given our site, you can see here how our site is, we're kind of collecting flow all the way along the perimeter. We're not going to change the size of that swale. So what I could do is I could lock that swale. So use it towards our goal, but don't change that size. Don't change the facility. So when we size this, you'll find we're going to be slightly over what we need to be. Well, about 1,500 cubic feet over, as we'll find. And we can get into, obviously, if you want to have different design levels or update areas, lengths, widths differently, right, you can customize this table. The defaults are, well, they're there for a reason. They're probably the most common things you would want to change for your facilities, but obviously each one can be independent. So we have our volume, the target volume. So this comes from, let's say, if I have my swale, right? So if I turn this back on, you'll see here is the runoff reduction volume. Here's the stormwater control volume. And ultimately, if you're going to have a facility which isn't locked or is not applied, we can see the value that's going to be required to change. So we need to get it up to these sizes. So that's it. So in one go, I can apply the sizing. Well, right away you'll see that I have met my goal. All the facilities are individually sized as big as they need to be, with a little extra because of that pond. So even just with this, I could I could report this right here and then go back to my plan view, and we'll see the changes which were made. So if I zoom in here, some of these items, well, they aren't too exciting, right? The porous pavement was pretty well spot on. You'll see it kind of amplified out a little bit, though I made sure that these rain gardens were undersized enough where we can really see a change happen. So we could lay these out differently. Big item here is you can see in the proposed plan there's a lot more rain gardens that were proposed. So what did I say? These facilities need to be about 2 to 3 times the size that they currently are. Well, you'll see there's 2 to 3 times more rain gardens, which were proposed, than I allowed. So we could either redefine some inflow areas and just simply add more rain gardens. We could reconfigure these rain gardens across our site, so on and so forth. So all in one go, we can see how far off we are, how well that design worked, or perhaps just adjust those constraints, maybe make them deeper. If you have a lot of swales, perhaps, which can be deeper, maybe underground storage facilities. Very quickly, we can design based on our site constraints. So one thing I mentioned was pipe sizing. I actually have a model I want to show, which is pretty complex. This happened to be a case study on a live project, and I'm not going to show, I guess, anything other than just this contour image. I'm not going to show any actual project information, but you get the idea. We have, this is something I've presented previously at some conferences, case study where we had assessment of pretty complicated overland flow, kind of high flow bypass, pipeline trunk systems. So let's look at sizing this whole facility at once. Okay, this is much more complex than our site is as far as the conveyance would go. So we can look at, so it's this trunk, this dark purple line, I'm calling the trunk system. We're going to size the main drainage path and all of the arterials. So the light purple branches, everything's going to be sized at once. So we'll see, I can select, right, this trunk, and we'll see a lot of information here. The main idea is how many barrels do we have and what are the diameter. And we can see that there's A for auto size. And we'll see it gives a breakdown of, right, the cumulative catchment area, the flow, proportional depth, what have you. And ultimately, we're going to find that we get some pretty large pipes. So 2 things we can do. Well, one, we can go to this pipe sizing criteria, and we can change how we're sizing this. So I have a number of IDF curves. I'm sizing this for a 5-year flows. Maybe this is a 10 or 20-year system design. We can also have different design constraints. We could have cover level, slope, velocity, and change soffits or obvert, depending on I guess what you were told in college, kind of the top of the pipe or the bottom of the pipe. So we can design for all these different systems, so the obverts or the soffits meet, or the inverts. So pretty detailed. By default, I'm just going to size up the inverts, so that's all flush. And that's what I used here. So one thing I could do, I said, I don't really want to have 96-inch pipes. So what if we started using perhaps multiple barrels? We can see what kind of difference, right, that would make if I, right, size again. I think I actually applied one of those design constraints because it, so they're sticking. But obviously, putting in the barrels is going to reassess the proportional, the design depth and the capacity, and give us our sizing accordingly. Again, this is based on the rational method and the Manning's equation. Okay, just for basic kind of the stock standard pipe sizing process. So just wanted to mention that. That's obviously much more complex pipe conveyance system than what we have here in our model. Back to this model, getting down into this detention pond. So if we were to run this model, we can look at beyond just the runoff reduction event, those higher protection events. first thing we might want to do would be to, under this analysis criteria, I have rainfall. So here is, I have a number of different rainfall patterns and types we could use. I happen to be having 2 different SCS areas represented here. I also have some HUF storms. If perhaps you're in, say, Indiana, and then HUF distribution is something you use. So all that information is here. So we could analyze this with HUF. I'm just going to use this Greenville area. And if we solve this simulation, take a second, I'm actually running 2 different design combinations. One we'll look at in a second. So run through all the different rainfall events for all the different design storms. So this is going to load the results. I'm going to look at really just this final facility. And at this facility, I guess the main thing I want to be looking at is that outfall configuration. So in most cases, you're going to probably have what I'd call a multiple outlet. So we're going to have not only a kind of high flow bypass, a high flow weir. And this is just a summary of all the controls. I'm going to ignore it for now. That's something we'll get into in the next webinar. But just for grins, we could look at and here's our rain garden down through our swale into our pond. You see how our system is operating. So I want to size this basin. Most important thing for sizing, I go back to the sizing calculator, is going to be the outlet, or perhaps one of these constraints could be side slope. Right, so I want to maybe keep the top area and have my side slope be, 1 to 2, so 0.5, or the opposite. I know what base footprint I want to start with. Could just be 0, and then go up at a certain slope. So we could do that. I'm going to focus on the outlet here. So let's look at a multiple outlet type. I believe I might have showed this already last time. We have a range of different outfall configurations. Just a weir, just an orifice could be used. Okay, I want to look at multiple. So let's add this from scratch. And I'm going to say that we have so I want a kind of low flow orifice and a weir. And I could individually use this calculator. I could individually size these based on design depth, based on the flow rate I'm expecting, coefficient, what have you. I can also do this kind of all at once. So here's this button here where I can just, in this table, I'm going to stick with the default coefficient of discharge. I'm going to say for the orifice, up to about 3 feet deep is my design depth. And I happen to have looked for, in the existing undeveloped conditions, we have about 6.5 cubic feet per second in the 5-year event. Okay, great. So for that high flow weir, for that 100-year event, okay, maybe that's kind of up there towards that, towards the top, towards the exceedance level of my facility, but I don't want to go into my freeboard zone. So let's just go 4.3 feet deep with 13.3 cubic feet per second. So I have some constraints based on perhaps my existing additions. Calculate that, and it's going to automatically give me my, for my diameter of my pipe, or for my diameter of my orifice. Same with the width of my weir. Now I could change this to be standard sizes, or add in additional controls to this facility. So I can add in additional items, V-notch weirs. We could even get into pumps if we wanted to. And so with this configuration, right, it gives me this table stage outflow. We can begin to assess and start looking at our peak events and compare those to the different phases. That's something we're going to look at a lot more next time in our next webinar. But this, I guess, is kind of the bookend for today that I wanted to show. So we talked about not only the orifices, or sorry, not only the outlets at the end, but also the, we looked at just briefly the different types of rainfall. Usually it's going to be something along the lines of a HUF or an SCS, most commonly in the U.S. Right? We can accommodate a range of different rainfall formats, obviously solve these different events with these different designs, and begin to size either individually or globally our system. So thank you all very much for joining today. I know there's a lot of information to get through in this amount of time, so I would be happy to discuss after the webinar. If anyone has any questions or like to maybe see a demo for their group, or just have an in-depth discussion on projects that they're working on, I'd be more than happy to discuss personally with you your own projects, or even just kind of show to maybe a larger group that didn't get to join today some of these items. So thank you for joining.